Some neurons have a tendency to produce rhythmic or quasi-rhythmic activity without input from any other neurons. If a neuron produces spontaneous rhythmic bursts of spikes when it's totally isolated from all other neurons, it's known as an endogenous burster. There's another class of neurons called conditional bursters, which can produce rhythmic bursts of spikes in isolation, but only if the correct combination of neuromodulatory substances are present in the bathing medium. Finally, there are neurons which are not spontaneously rhythmically active, but which produce a sustained depolarisation leading to a single burst of spikes. This occurs in response to a brief depolarising input. Such sustained depolarisations are called plateau potentials. There are several different mechanisms which can give a neuron properties such as these, but they all share the basic features of a relatively slow, voltage-dependent, regenerative, depolarising current, which in turn activates a slow, restorative, hyperpolarising current. The neural model used in AnimatLab implements one of the simplest such mechanisms, a slow, voltage-activated calcium current, which has even slower voltage inactivation. This is probably oversimplistic, but it gives a good first approximation to bursting mechanisms. This tutorial will demonstrate how to build endogenously bursting neurons for use in your AnimatLab projects. Let's begin by creating a new project. You can find a copy of this tutorial at Program Files, AnimatLab, Tutorials, Neural Networks. Choose where you want to create this project and name it Endogenous Bursters. Once you have a project, you need to add a new organism and open its behavioral editor. Then add a spiking neuron. The properties for controlling the calcium current are found in the bursting properties section. It consists of a set of properties that controls calcium channel activation, another set for channel inactivation, and a maximum calcium conductance value. Set the calcium conductance value to 18 microsiemens. This sets the calcium conductance when all calcium channels are fully activated. The activation and inactivation parameters control the channel's kinetics. The calcium current has a defined equilibrium potential which is located in the global properties section of the neuromodule. Activation and inactivation both have first-order kinetics. Each variable has a defined midpoint voltage at which it has a steady-state activation value of 0.5, a midpoint slope which describes the rate of change of the variable with voltage at the midpoint, and a time constant which describes the rate at which the variable approaches its steady-state value. Set the activation slope to 0.12, the activation time constant to 8 milliseconds, and the inactivation time constant to 2000 milliseconds. Next, we need to create a chart so we can watch the memory voltages of our neurons. Set its end time to 2 seconds. Collect data interval to 0.2 milliseconds. Points to keep to 15,000, and update interval to 250 milliseconds. Run the simulation. We get a nice series of bursts for a neuron with a frequency around 3 bursts per second. Let's take a closer look at how this oscillation is being produced. Let's apply TTX to the neuron. TTX blocks voltage-dependent sodium channels. This eliminates the ability to generate action potentials, but leaves other currents intact. When we run the simulation again, we can see that the underlying membrane potential oscillations are slow, repetitive spikes, but that the inward current is carried by the calcium rather than the sodium, and that the termination of the depolarizing phase is simply brought about by inactivation of the inward current. Now let's remove the TTX and apply cadmium instead. Cadmium blocks calcium channels while leaving other currents. When we do this, the neuron just sits at its resting potential with no oscillatory behavior. Take the cadmium off It's also possible to reset the cycle of an endogenous burster using a current pulse. Add a new tonic current stimulus to neuron 1. Set its start time to 1100 milliseconds, end time to 1200 milliseconds, and amplitude to 5 nanoamps. Run the simulation. This time, at 1100 milliseconds, the current pulse caused a new burst to start and reset the cycle. Knowing how to get a neuron to burst is important, but it's also important to know how to control it. This means being able to determine the burst duration and the interval between bursts. So how is this accomplished? Let's disable the stimulus we just added in. And then increase the end time of our chart to 5 seconds. We'll be collecting more data now, so increase the points to keep to 25,000. Rerun the simulation so we can see it for this longer time period. Now set the calcium inactivation time constant to 10,000 milliseconds. Essentially what we're doing here is increasing the time it takes for our calcium channels to inactivate. If they inactivate more slowly, then the neuron will remain depolarized for longer and the burst will be extended. This time we barely get 1.5 bursts per second, and the burst duration has increased greatly. It's also possible to control the interburst duration. We can do this by changing the activation time constant. Let's set it to 200 milliseconds. Now we only get one burst every 2 seconds. Increasing the activation time constant increases the time it takes for the calcium channels to activate, and this means it takes longer to reach the point where they'll begin bursting. You can use these mechanisms to build bursting neurons that meet your needs. You can also create neurons that demonstrate plateau potentials. These neurons don't oscillate like the examples we just looked at. Instead, they produce bursts of spikes for a short period of time when stimulated with a brief depolarisation. Let's begin by setting the activation time constant back to 8 milliseconds and the inactivation time constant to 2000 milliseconds. Then change the activation midpoint parameter of the calcium current from negative 30 millivolts to negative 25 millivolts. This change means that it now requires just a bit more depolarization to activate the calcium current. When you run the simulation this time, the neuron depolarizes slightly, but it doesn't burst. Now let's change the end time for our current stimulus to 1110 milliseconds and then re-enable it. Now when the current pulse is applied, we get a period of bursting. Let's move on to the more abstract firing rate neuromodels. Begin by first closing down the current data chart. Then add a pacemaker neuron to the diagram. The oscillatory behavior of this pacemaker neuron is much simpler than the one we just got through looking at. It's basically programmed to have two states that alternate back and forth using some hard-coded transition rules. In each state, an intrinsic current is applied to drive the membrane voltage to oscillate. This neuron tries to emulate a number of key properties of rhythmic neurons. First, when the pacemaker is sufficiently hyperpolarized, it's silent. Second, when the pacemaker is sufficiently depolarized, it fires continuously. Third, between these two extremes, it rhythmically produces a series of relatively fixed duration bursts. The length of the interval between the bursts is a continuous function of the injected current. Fourth, a transient depolarization which causes the cell to fire between bursts can reset the bursting rhythm. Fifth, a transient hyperpolarization which prematurely terminates a burst can also reset the bursting rhythm. For this pacemaker, the burst duration is explicitly provided by the user. The parameter T sub h specifies the duration of the burst, and I sub h is the intrinsic current that is active during this time. The interburst duration is slightly more complicated. The duration between bursts is calculated using a linear equation that depends on the steady-state membrane voltage. The steady-state membrane voltage is the voltage you get when you don't consider capacitive effects. It can be calculated using the input current and the membrane conductance. A slope and intercept value are also needed to calculate the interburst duration. These are provided by the user. You can adjust the values to get a desired frequency at a given current. For example, if our membrane conductance is 100 nanosiemens, slope is negative 100, and intercept is 2 seconds, and we assume that our input current is 0.5 nanoamps, then we can calculate that the steady-state voltage is 5 millivolts. Plugging this into our equation, we end up with an interburst duration of 1.5 seconds. Now let's set our pacemaker to match these values. Set the intercept, B sub TL, to be 2 seconds, and change the gain to 10. The rest of the parameters are correct. Now add a new chart, and add items to view the firing frequency, membrane voltage, intrinsic currents, and external currents. Set the points to keep to 15,000. Now run the simulation. Unfortunately, we didn't get any bursting. So what exactly happened? The problem is that this neuron defaults to not burst without some type of a stimulus. This property is controlled by the parameter called V sub SSM. If the membrane voltage of the neuron is below this value, then the low cycle current is locked on. Notice that the intrinsic current is at negative 2 nanoamps. Let's temporarily set this value to 0 and rerun the simulation. This time we get bursting. Now set V sub SSM back to 0.1 millivolts. And let's add a current stimulus to the neuron and name it A. Set it to end at 10 seconds and with an amplitude of 0.5 nanoamps. Run the simulation again, and this time we get bursting. Also, you can see that the interburst duration matches our calculated value of 1.5 seconds, and the burst duration is 1 second long. Now let's change the chart's end time to 20 seconds and add another stimulus. Set its end time to 20 seconds, start time to 10 seconds, and amplitude to 1.5 nanoamps. When we inject more current, the inner burst duration is reduced and we get a higher frequency. This demonstrates one of the properties that we mentioned. The length of the interval between bursts is a continuous function of the injected current. Greater current means a reduced inner burst interval. Add another stimulus and set its end time to 17. Start it at 15 and have an amplitude of -5 nanoamps. This demonstrates another of the properties we discussed. A transient hyperpolarisation prematurely terminates a burst and resets the bursting rhythm. Change the chart end time to 45 seconds. And add a new stimulus. Set it to have an end time of 40 seconds, a start time of 20 seconds, and an amplitude of 0.2 nanoamps. When the current is reduced, we get a shorter frequency. Now let's add two new stimuli. The first has an end time of 28.8 seconds, a start time of 28.5 seconds, and an amplitude of 5 nanoamps. The second has an end time of 37 seconds, a start time of 33.5 seconds, and an amplitude of 5 nanoamps. Let's run the simulation again. This demonstrates the last two properties of the bursters. The first is that a transient depolarisation can cause the cell to fire between bursts and reset the bursting rhythm. The second is that when the pacemaker is sufficiently depolarized, it fires continuously. This tutorial has demonstrated a variety of different endogenous bursting systems and has shown you how to control them by setting properties like the burst duration and inner burst interval.